Welcome to This Explainer. Okay, today we are going on a totally fascinating journey. We're going to take a concept that usually just lives in the dusty pages of chemistry and physics textbooks and trace it all the way to the absolute cutting edge of modern artificial intelligence. We are talking about entropy. Now, you've probably heard the word thrown around, but by the end of this explainer, you're going to see exactly how the universal law that governs a melting ice cube is the exact same mathematical engine powering the AI algorithms shaping our world right now.
But before we get to the AI stuff, I want to challenge your everyday assumptions for a second. Take a moment and really think about this question. Which of these two things is more disordered? On one hand, you have a jagged, chaotic cup of crushed ice. On the other, a smooth, calm, perfectly uniform glass of room temperature water. I mean, it seems super obvious, right?
Well, if you guessed the crushed ice, you are in really good company, but you're actually wrong. The glass of room temperature water has higher entropy. Entropy is notoriously difficult to wrap our heads around, mostly because we're taught to think of it just as visual disorder. But that is a terribly misleading illusion. The crushed ice might look messy to our eyes, but on a molecular level, the energy is much more locked down than in the liquid water. Entropy isn't about looking messy, it's about something much more profound.
Okay, let's dive into this. Here is our roadmap for today. We'll be hitting the illusion of disorder, microstates and probability, information and uncertainty, AI decision-making engine, and finally, optimizing models and challenges.
Starting off with Section 1, the illusion of disorder.
So, if we strip away that whole misleading idea of things just being messy, what is entropy? Technically, it is a direct measure of an energy configuration's probability. Basically, it tells us how spread out or concentrated energy is in a system. When entropy is low, it means the energy is highly concentrated in one place. When entropy is high, it means the energy is widely spread out. The universe simply prefers energy to be spread out. But to really grasp why that is, we've got to look a bit closer.
Let's build a mental picture here to visualize the invisible. Imagine two very small, simple solids right next to each other. We'll say each solid has exactly 6 atomic bonds. You can think of these bonds just like little containers. Now, these containers hold indivisible units of energy, which scientists call quanta. And the more energy, or quanta, a solid has, the hotter it is. A microstate is simply one specific, exact way that you can arrange these units of energy among those container bonds.
Now here's where it gets wild. Just look at the sheer scale of possibilities. 9,702. Let's say we put 6 quanta of energy in solid A and just 2 in solid B. Even in this incredibly tiny, super simple system, there are exactly 9,702 microstates. That means there are 9,702 different ways those specific units of energy can be mathematically arranged within the bonds of those two solids. If we arrange the energy differently, say putting all 8 units in solid A and 0 in solid B, there would be a completely different and much smaller number of microstates. Ultimately, entropy is directly tied to how many microstates an arrangement has.
All right, Section 2, microstates and probability.
In the real world, energy doesn't just sit still. It is continuously hopping between neighboring bonds. And this brilliantly illustrates what happens when it does. Because energy is constantly shifting, the arrangement changes based purely on probability. In our tiny little system, there is a 21% chance the energy spreads out even further, simply because there are more microstates, more possible combinations for dispersed energy. There's only a 13% chance it returns to its exact starting distribution. And remarkably, there's actually an 8% chance that the hotter solid A arbitrarily absorbs more energy and gets even hotter.
Wait a minute, an 8% chance a hot object just randomly gets hotter? Why don't we ever see a hot cup of coffee suddenly start boiling on your desk while the rest of the room freezes solid? Well, it's entirely about scale. If we scale our hypothetical solids up to just 6,000 bonds and 8,000 units of energy, the chance of the hotter object spontaneously acquiring more energy shrinks to an infinitesimally tiny number. And familiar everyday objects? They have millions and billions of times more particles than that. The probability is so absurdly small that it simply never happens. Energy spreads out because it's statistically inevitable.
Which brings us to Section 3, information and uncertainty.
Back in the mid-20th century, a mathematician named Claude Shannon realized something amazing. This exact same mathematical concept of probability could be applied to digital information. Instead of measuring the uncertainty of where physical energy is located, Shannon used entropy to measure the uncertainty of information. Think about flipping a perfectly fair coin. Before you flip it, you have maximum uncertainty about the outcome, right? It is equally likely to be heads or tails.
Well, in information theory, the entropy of that single coin toss is exactly 1 bit. It takes exactly 1 bit of information to resolve that uncertainty.
So let's connect the dots here. Physical entropy measures the spread of physical energy based on the probability of those microstates we talked about. Shannon entropy, on the other hand, measures the amount of information needed to describe outcomes, essentially quantifying our surprise or uncertainty. But here is the kicker. The underlying math, the heavy reliance on probabilities, and the drive to calculate the most likely state is completely identical. Whether you're tracking a melting ice cube or a digital coin toss, entropy is literally the mathematical language of uncertainty.
Okay, moving fast now. Section 4, AI Decision-Making Engine.
So how does an AI actually use this in the real world? Picture a spam filter that uses a decision tree algorithm. When an email arrives, the AI has high entropy. It is highly uncertain if the message is spam or not. So, step 1, it calculates the entropy of the potential outcomes. Step 2, it looks at features. Maybe the word free is written in all caps to see how well that specific feature separates the data. And step 3 is where the magic happens. The algorithm deliberately chooses the mathematical path that results in the greatest reduction of uncertainty. It is systematically destroying entropy until it reaches step 4, confidently classifying the email. The AI is literally navigating its choices by trying to reduce its own mathematical surprise.
But wait, it doesn't stop at decision-making. Entropy is the absolute secret sauce in data compression, which is absolutely vital for modern AI. Techniques like Huffman and arithmetic coding use entropy to represent data using minimal space. How do they do it? By assigning much shorter digital codes to the most frequent characters and longer codes to the rare ones. It packs the data down perfectly without losing a single drop of actual information, what we call lossless compression. So whenever you hear about those massive AI models training on terabytes of text, it's entropy-based compression that makes storing and handling that colossal amount of data practically possible in the first place.
And finally, Section 5, Optimizing Models and Challenges.
A really crucial point is how we actually evaluate if an AI is learning anything at all. We use a metric called cross-entropy. Imagine you're training an AI to recognize images of cats. Cross-entropy compares the predicted probability distribution, basically how confident the AI is that the image is a cat, against the true distribution, which is the actual 100% reality that yes, it is a cat. Cross-entropy serves as what we call a loss function. The higher the cross-entropy, the worse the AI is doing. The entire goal of training a neural network is to optimize the weights to minimize this cross-entropy loss, forcing the AI's guesses to align flawlessly with reality.
And data scientists have some seriously powerful tools at their fingertips to do this. If you're coding in Python, libraries like NumPy and SciPy offer direct entropy calculations for feature selection. The R programming language has dedicated entropy packages for seamless workflow integration. And the absolute heavyweights in the field, like TensorFlow and PyTorch, they have built-in cross-entropy loss optimization right out of the box. These are the daily instruments professionals are using to wrangle uncertainty into true artificial intelligence.
Now, to be totally fair, entropy isn't just magic, and it comes with some very real challenges. Calculating entropy across massive real-world datasets is incredibly computationally intensive. I mean, it takes a ton of processing power. On top of that, entropy alone doesn't always capture every single nuance of uncertainty. In highly noisy data environments, distinguishing the truly meaningful information from random static is really tough. Developers are constantly playing this massive tug-of-war, trying to balance the mathematical precision of entropy calculations with the blazing fast efficiency required for real-time AI applications.
But despite all those challenges, it remains a completely foundational pillar of science and technology. As our source material so eloquently puts it, that's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will. It really is a universal rule. In the physical world, it dictates the inescapable flow of heat and time. And in the digital world, it quantifies the exact boundaries of what we know and what we don't.
Well, we've covered a massive amount of ground today. We've gone all the way from atomic bonds holding invisible units of energy to Claude Shannon's coin tosses, straight through to the cross-entropy loss functions that are literally training tomorrow's neural networks. So, now that you understand this hidden mathematical secret connecting the physical and digital universes, how will you leverage uncertainty in your next AI project? It's definitely something to think about. Thank you so much for joining me for this explainer, and keep exploring.